Good morning. I'm Stefan Werkstatter, VP of Sales EMEA at EPC, and welcome to today's webinar, Ultra Compact DC-DC Converters with GaN. This is the second in a series of EPC webinars, and we'll discuss how GaN-based reference designs help to meet higher demands of today's power converters across a myriad of applications, power levels, and topologies. Before we get started, I would like to go over a few housekeeping items for today's event. You'll have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. You may send your questions in at any time. We will collect these and address them during the Q&A session at the end of today's presentation. Now, I would like to introduce our speaker today, Tiziano Morganti, who is our Senior Field Application Engineer at EMEA. Thank you.
Good morning. Let's start the presentation. Brief summary of what we will talk about. Basically, quick background about our GaN FET technology and ICs, the evaluation tools we have, and then we will see some experimental examples of our demo boards, and then we will conclude our presentation. So basically, our GaN FET is a transistor, so it's a three-terminal device, is controlled by voltage, and it embeds a reverse diode function. Basically, this is the symbol. So we have gate, source, and drain. The current between drain and source is controlled by a voltage between gate and source. Basically, what is gate to source voltage doing is modulating the conductivity of the channel of the transistor. And we have the third quadrant conduction mode, in which the current is still carried by the channel. So we have majority carrier transport as diode function with no reverse recovery. EPC offers GaN FETs in chip scale package, which is a bare die with bumps termination to be soldered on the PCB. And we have both ball grid array style and lately land grid array style. We also have an offering in QFN package, which is, in example, this EPC2302. GaN versus silicon. So what are the difference between our transistors and the silicon MOSFET? So basically, GaN is a material that allows much smaller device for the same RDS(on) area. And so we have a figure of merit, which is the ratio between the RDS(on) per square millimeter of device, which is much better than silicon. So it's depending on the voltage level, in the 100 volt VDS ratings range, we have about 4 times smaller devices compared to silicon. In the 200 volt, we have 16 times smaller devices compared to silicon, same RDS(on). Gate charge is much smaller, 5 to 10 times. We are fully turned on at VGS 5 volt and fully turned off at 0 volt. So we recommend 5 volt for turn on and 0 volt for turn off. And this means the gate power loss is reduced by a factor of at least 10 compared to silicon MOSFETs. We have much smaller QSS, from 2 to 4 times, depending on the voltage ratings on the drain to source. We have much smaller switching charges. So QGD is the Miller charge, and it drives the DVDT, so the transition on the voltage. And QGS2 is the threshold to plateau charge, which drives the transition on the current. So those are much smaller, and so we can get very fast transition on the voltage and current. So very fast switching. We have zero recovery on the third quadrant. diode function. So all those factors are enabling much higher frequency operation compared to silicon. And we have also been a lateral technology. We can also integrate more devices in a single die. So we can integrate gate driver and logic to build a power stage IC. An example, we have those power stages. The first one here is dedicated to LiDAR applications. And it is a low side switch with integrated gate driver, while the other ones are half bridges power stages with integrated gate driver with level shifter, synchronous bootstrap rectifier, and input logic. So basically, you can connect directly to logic level microcontroller output, PWM output on this side, and you get the power switching on this other side. What are the advantages? Basically, we have zero common source inductance, so the gate loop drive is fully decoupled from the power loop, being integrated into the device. The gate driver is matched to the power FET, and we have a form of thermal balancing for the half bridges. So if you have asymmetric heating of the two power devices in the half bridges, they share a common die, so they will equalize the temperature between themselves. And it is layout friendly, so it's much easier to lay out, and this also contributes to lower parasitics in the layout. In terms of evaluation tools, we have basically two series of development boards. One is the 9000 series. Those are basically half bridges that can be used to show an example of layout for all of our devices. And they can be also used as a building block to evaluate the performance of our devices. So they usually do not include magnetics and bypass capacitors on the output. They include the bypass capacitors on the input bus. And so it's basically an half bridge building block that can be used to implement buck converters, boost converters, or full bridge converters with two of them. Also, we have demonstration boards, which is the 91XX series. So those are fully functional demo circuits with full functional converter. And we have also documentation and schematics and Gerber's file on our website. We can also share the Altium files. In this presentation, we will show a few of those demo boards. We will see two-phase buck converter, EPC9151. We will have a look to a more powerful dual-phase bidirectional buck boost converter, EPC9165 and EPC9170. Then single-phase buck converter, which was developed for being very compact and low profile, EPC9177. And then we will have a look to bus converter, which is EPC9159, which is very high power density bidirectional LLC converter. Let's start with the EPC9151. This is a 300 watt, 1/16 of brick, two-phase interleave buck converter, and it is digital control. The specifications are like in this table. So we have input voltage from 18 to 60 volt. Output voltage is from 5 to 15, and the standard controller is programmed for 12 volt output. regulated. And it can also work in boost mode, so it's a bidirectional implementation. So in this case, with input voltage between 11.3 and 15, and output voltage regulated to 48 volts. Output power is up to 300 watts, and the switching frequency is 500 kilohertz, and the size is as reported in the table. It is based on a monolithic power stage, which is EPC9152. So this is an 80-volt half bridge with 10 million FETs in a chip scale package. Then let's have a look to the topology. So it's a two-phase converter. So we have two of those power stages with two inductors, two current sense, and bypass capacitors, and the microcontroller is providing the input signals to control each of the two power stages. And we have an housekeeping power supply, which is powered both from the output and from the input to be able to start up in either of the directions. So it's either back mode or boost mode. So with the two-phase converter, we can reduce the size of the inductors, and the ripple can be cancelled if you interleave the two phases. We have a reduction of the RMS current for each of the inductor, and we can reduce the ripple current. And another advantage of the interleaved solution is that the power dissipation is distributed across more devices, and so it's easier to cool it down. Also, in case of low load conditions, you can fully switch off one of the two phases to reduce the losses in the output capacitance and to improve the efficiency. This is the board. So the top view of the board. So we have the bottom view with the controller. So let's have a look to the components. So this is the power stage, EPC9152. Then we have the two inductors. This is the housekeeping power supply. We have the output capacitors on the bottom side, and this is still part of the housekeeping power supply. We have the input bypass capacitors. This is the microcontroller. We use microchip DSPIC 33CK. And these are the current sensors for the output. In back operation, this is the efficiency we can get. The output current is up to 17-18 amps with 400 linear feet per minute airflow with more than 95% efficiency. With more airflow, so 1700 linear feet per minute, we can go up to 25 amps output. In boost mode, we still get more than 95% efficiency, and we can handle more than 5 amps output current. Thermal imaging of the board delivering the full power output. So we can see the temperature is under control. And so you can see the hotspot is on the power stage is 88 degrees with ambient temperature of about 25 degrees. Let's have a look to the more powerful EPC9165 and EPC9170. So this is designed for automotive application 48 to 12 volt bidirectional conversion. Okay, so the specs are as reported in this table. We have a high voltage port, which is from 20 volt to 60 volt. Low voltage port is from 11 to 16, and it's designed to regulate at 14.4. The output power is up to 2000 watts, and the switching frequency is 500 kilohertz. The board is based on the EPC9302, which is a 100 volt, 1.8 million max QFN package FET. And the EPC9170 is using the integrated power stage EPC23101, which is integrating the I-side FET, which is a 3.3 million 100 volt rated, and also the gate driver, also the gate driver for the low side FET. So basically, those two components together builds a power stage. So it's a two device chipset for an half bridge power stage. This is a picture of the board. So you can see the output inductors. This is the top side with the heatsink. Below the heatsink, there are the GaN FETs. And on the bottom side, only for the EPC9165, we have the gate driver. The 9170 is based on the power stage, so there is no gate driver underneath. So those are the input terminals, output terminals. Those are just in parallel. And this is the housekeeping power supply. Current sense amplifiers, those are the current shunts for measuring the output current. Output current is up to 70 amps per phase. This is the heatsink and the gate drivers. The controller is this external board, the EPC9528. We are using it on several of our demo boards. And the expansion port to connect two cascaded EPC9165 or 70 boards to be able to implement a 4 kilowatt converter. So this is an overview of the power stage. So we have the EPC2302 on the 9165. We have the chipset, so EPC23101 and EPC2302 on the EPC9170 board. On the bottom side, only on the discrete FET design, we have the gate driver. We are using monolithic power system MPQ1918, which is automotive qualified. And in the power stage based board, there is no external gate driver because it's integrated in the 23101. We have temperature sensor underneath the heatsink. We have spacers with M2 threads to mount the heatsink on the top side. Then an overview of the inductor. So we were using in the past, in the first version of the boards, Vishay molded inductor, which was showing higher losses in the core. So we upgraded our boards with this custom inductor, which is based in a gap ferrite core, and it's slightly higher inductance. It's 1.3 microhenry, and it's holding its inductance up to higher level of current, so with a minimal drop at 80 amps. It's a low DC resistance, 0.64 million, and it is very low AC loss. So we tested our boards. Our usual way to test them is two boards. One is configured in buck operation, the other one in boost operation, and we connect them in a back-to-back mode of operation. So basically, the buck board will generate a 12 volt output or 14 volt output in this case, and this output is feedback to the boost operated board, which is connected back to the 48-volt bus. An external power supply is needed just to cover the power loss. So basically, the energy, the power is recycled by this loopback configuration, and the external power supply is just supplying the losses. So we tested in this way the efficiency, the balance of the current of the two phases, load transients, and startup operation transient. So this is the efficiency we could measure. So we have in back mode, we have more than 97.5% efficiency at peak, so almost 98% peak efficiency, dropping to 96.5 at full load. The plot here down is showing the losses in the full board. So this efficiency plot is including also the controller. So it's the full system efficiency. Thermal imaging of the boards. So you can see we have some airflow, I think 800 linear feet per minute on this board. And we measure the temperature of the power stage on the back of on the bottom of the PCB. So we could see the hotspot temperature being about 80 degrees. So yeah, this is an approximate measurement of the temperature of the power stage, but it is yeah, we can also measure the temperature of the power stage with special very small optical temperature probes, but this is the easiest way to assess the results, and the temperature underneath the PCB is pretty close to the die temperature. This is the EPC9170, which is a slightly higher temperature than the discrete implementation board. And this is the configuration where you can cascade two of those boards, and a single controller can control two of those boards, and you can build a 4-phase system with up to 4 kilowatt output power. Okay, let's go to the 9177. So this has been developed for a very compact application. So it's a very small PCB PCB estate occupation, and very low profile. It's a synchronous buck converter with a single phase. So the input voltage is from 12 to 64 volt, and the output voltage is regulated to 12 volt. We switch at 720 kilohertz. The board is featuring our power stage EPC23102, which is 100 volt, 6.6 milliohm for each power FET. And it integrates the half bridge gate driver and the level shifter and synchronous boot rectifier. This is the picture of the board. So we have the demo board. The area where the design is fitted is 21 millimeter by 13 millimeter. The inductor, which is the tallest component, is about 3 millimeter tall. So it is a very compact design. So this is the power stage, bypass capacitors, and we have on the bottom side we have the controller, the current sense, and the housekeeping power supply. This is the solution for the additional optional heatsink. So we have a thermal interface material, two parts of it, one thicker for the power stage, one thinner for the inductor. Then we have a copper heat spreader, which is matching the height of the components. And then we have another thin thermal interface material and the heatsink on top. So with this heatsink, we can extend the current output of the converter. Tests. So we have the green plot is 24-volt input with up to 15 amps current output without the heatsink. And then we have the blue plot is 36-volt input, which is higher than 96% efficiency, up to 15 amps with no heatsink. And finally, at 48-volt input, we have about 95.5% peak efficiency, and the current output can be extended to 20 amps with additional heatsink. And on the right plot, you can see the power losses of the converter, and this is including the controller, so it's a full system efficiency. This is a thermal image with airflow, so it's 15 amps output, and you can see the temperature rise is around 60 degrees compared to ambient. Finally, let's have a look to our EPC9159, which is a very high power density bidirectional bus converter. So it's 48 to 12 volt fixed ratio LLC converter. The specs. So the power stage is a 3-to-1 fixed ratio converter. So nominal is 36 to 12. And it can work from 24 up to 42 volt input. And the input to output ratio is fixed at 3-to-1. The converted power is 750 watts. The switching frequency is 1.6 megahertz. The thickness is 8 millimeter, and the size is 22.8 millimeter by 17.5 millimeter. It's a very small power converter. So the power density of this converter is about 4 kilowatt per cubic inch. In terms of topology, so this is a full bridge high voltage side LLC converter with center tap synchronous rectification at the low voltage side. So the primary current is shared by 4 devices, so 2 legs, so it's a lower current. We have no DC component across the resonant capacitor. We have both an additional external inductance and the leakage inductance of the transformer to constitute the resonant tank of the LLC converter together with the resonant capacitor. And we are using the magnetizing inductance to achieve 0 voltage switching at the primary side. On the secondary side, we are using 3 parallel FET for each leg. And yeah, the output current is up to 63 amps. So the system is fully featured, so it has gate drivers and power stages and magnetics, and the digital controller is on an external board. We used as power devices on the primary side EPC9165, which is our latest generation technology, which is generation 6. It's a 100 volt device, 3.3 milliohm typical, and it is only 1.5 by 2.5 millimeter. On the secondary side, we are using EPC9165, which is a 40 volt device, 1.55 milliohm typical in generation 5, and it is about 9 square millimeter. So we have reduced size of our dies for the same RDS(on) compared to silicon MOSFETs. We have much smaller gate charge, and this allows switching at 1.6 megahertz without excessive gate drive losses. And we can drive the gates at 5 volt only, which simplifies the design. And we have also lower output charge that makes easier to achieve 0 voltage switching. We have low gate to drain capacitance and no reverse recovery. And this helps in the synchronous rectifier side. So we can get a smaller solution with much higher power density compared to silicon MOSFETs. So why we designed a 3-to-1 converter for a 48 to 12 volt operation? Because we are using this configuration. So the 3-to-1 converter is basically connected. So the input port is connected between the input voltage and the output voltage. So in this way, the input current is fed to the output, so it is passed through without loss, basically. And the output current of the 3-to-1 converter is then added to the output port. So in this way, we have designed this 3-to-1 module. So 36 volt input, 12 volt output. The 12 volt is also in this node. So we have a total of 48 volt input voltage to the system. Yes, as we said, the 12 volt output is elevating the low side terminal of the converter. So basically, in this configuration, the module is processing only 75% of the power, of the output power. And the remaining 25% is passed through with virtually 100% efficiency. This is the power module, full bridge board. And this is the board with the magnetics. We had to integrate the secondary side synchronous rectifier within the magnetic windings to reduce and minimize the leakage inductance and the voltage spikes on the synchronous rectifiers. So this is the input port, and this is a transformer which is capable of transferring 750 watts. Those are the 4 by EPC9165 GaN FETs. Those are the 3 parallel on top side plus other 3 on the bottom side EPC9165 synchronous rectifiers. Those are the gate drivers for the top half bridge and bottom half bridge. This is the transformer, which is a custom core. And we have a connection from the full bridge to the transformer. This is the PCB of the transformer assembly. So you can see those are the resonant inductors, resonant capacitors. We are using U2J capacitors for this purpose. And those are the synchronous rectifiers. This is the test board. So we have split the design with the purpose to be able to test all the signals and to do all the measurements, and the controller is external. It is still the EPC9128 board. So this is the transformer module, primary full bridge, 48-volt connection, 12-volt connection. This is the mode selector, so you can configure the board to operate in partial power mode or normal conversion mode. And this is the controller and the programming port for the controller. We have test points to do Kelvin measurement of input and output. So we do not provide the chance to measure the current. The probe points, we have the FET drains on the primary side, the PWM signals from the controller, and we tested efficiency, load transients, startup, and power flow modes. Basically, this is the efficiency in partial power mode, 48 volt to 12 volt. So we reach 98% peak efficiency. And we drop to more than 96% efficiency at full load. This is an example of the waveforms from no load to full load. This is a thermal image of the system operating at full load. So you can see, we add some airflow, and you can see temperature is under control. Okay, so let's get to the conclusion of this presentation. So basically, we have seen our GaN FETs and ICs can switch with lower losses and can enable higher frequency operation. So this can improve the converter efficiency. We can increase the power density. Then the ICs can simplify the designs and reduce also the full size of the solution, as we have seen in the 9177, because they integrate basically driver and more functionality. So we have seen 300 watt 116 brick two-phase interleaved buck converter, 2 kilowatt two-phase interleaved bidirectional converter, 240 watt synchronous buck converter with very low profile, and very high power density bidirectional 48 to 12 LLC converter. Okay, so thank you for your attention, and the presentation is over. Thank you.
Thank you, Tiziano. So now we are going to begin answering the questions submitted during today's presentation. You can still submit questions by typing the questions to the Q&A feature at the bottom of the screen. And so, Tiziano, the first question is, why are data centers increasing the bus voltage to 48 volts?
Well, this is pretty simple, because the power consumption of the digital ICs, CPUs, and GPUs and AI processors is increasingly high. So it's in terms of power, hundreds of watts. So if you want to bring hundreds of watts on a motherboard, if you do at 12 volt as in the past, it's going to be a lot of current. So a lot of current means a lot of copper and a lot of power loss between the main power supply and the motherboard. So if you increase the distribution voltage to 48 volt, you can reduce by a factor of 4 the current, and you can get to more efficient power distribution in the system. So from the main power supplies to the server motherboards. So this is the reason.
Next question. When do you expect to offer eGaN with RDS on below 1 milliohm?
We are working on it. We have first alpha samples of 80 volt sub-milliohm device. So it's going to happen likely next year. Maybe it's not lower than 1 million, but it's around 1 million typical RDS(on). So it's a generation 6 power devices.
Thank you, Tiziano. Next question is 1700 LFM needed for the 1/16th brick solution? That is a huge amount of airflow.
Yes, it's a lot of airflow. You can still reduce the rate of the current and use more reasonable airflow on the solution, or use add an heat sink on it. That's it.
Next question. Was the efficiency on slide 22 for both buck and boost or individually? What are the major contributors to the power losses?
Let me go to slide 22. A moment. 22, and this is the 2 kilowatt power converter. Wait a moment, let me share again the screen. Okay, hope you are seeing my screen now. Okay, so yes, this is buck mode. So it's buck mode, and the two plots are the green one is the EPC9170 with the IC power stage, and it's dropping a little bit in efficiency towards full load because the top side device is 3.3 million. The blue one is the discrete solution. So it's a buck operation.
And probably last question, what is the maximum switching frequency limitation for EPC new products?
Maximum switching frequency limitation? It depends on the losses and on the thermal management. I mean, our devices yeah, can switch really fast, especially the small ones. We have applications where they are switched at 50 megahertz, power conversion applications, in tracking converters for 5G radio stations. But it depends. It really depends on the device and on the thermal management. So if the device is very small, it can switch at tens of megahertz. For the bigger devices, we can switch at 500 kilohertz plus, and in soft switched converters, like we have seen the 9159, 1 megahertz plus switching frequency is possible.
Okay, thank you, Tiziano. And also thank you everyone for attending today's webinar. If we did not have a chance to answer your question, we will reach out to you with a response. Likewise, if there are any additional questions, please send them to info@epc-co.com. I repeat, info@epc-co.com. You will receive a follow-up email within 24 to 48 hours with a link to the video of today's webinar. And our next European webinar in November will focus on practical applications of GaN for motor drives. And registration will be open on our website soon at epc-co.com. Thank you for joining today's webinar and have a great rest of the day. Bye-bye.
Thank you. Bye.